Okay, here's a follow-up to the density of water lab. This time I took out the tub with the ice in it. This sat in the freezer overnight. And you can see that the top, it didn't really freeze flat across. There's a bit of a meniscus, and that's going to make the measurement of the height a little problematic. So I will pause this and cut off the plastic so I don't embarrass myself. I better work fast since it's already melting, and that means I'm changing the thing that I'd like to measure. So what we have for the mass here. Check that out. I poured water onto a scale and it's not even spilling. 547 plus or minus 1, of course. And now I'm calling the top diameter D1 and the bottom D2. I guess the top would be the bigger one. Where's my ruler? Okay. And this is going to involve some parallax error, meaning I may not have the numbers lined up exactly with the edge of the ice. And it looks to me like we've got something like 10.2 centimeters. And there's easily a couple millimeters of uncertainty there. So I'll go with 10.2 plus or minus 0.2. And then, oh darn it, how am I going to do the bottom? Am I going to have to hold this in my hand? Okay, I won't be a baby about it. 0.6, and this one's easier to measure. It's easier to be accurate, so I'll say 8.6 plus or minus 1 in this instance. Plus or minus 0.1, excuse me, just 1 millimeter, which would be 1/10 of a centimeter. And before I turn off the camera, take a look at the fact that the top is really not flat. In fact, there's a raised portion in the center that may even be as much as a centimeter, almost a centimeter. And it's probably more difficult to tell, but even the bottom is not particularly well defined. There's kind of an indentation towards the center. So I would say that the height of this whole thing is probably also uncertain by as much as a centimeter. Maybe half a centimeter would be more reasonable. So let's throw this into the spreadsheet now and calculate the density. I just realized I forgot to show you the measurement of the height. This is what I came up with, but like I said, the height was fairly poorly defined because of that bump on the top and the indentation on the bottom. I went with only half a centimeter absolute uncertainty, and that's because I chose a height that was in the middle of the possible range there. And yesterday I worked out using calculus the formula for this shape, this truncated cone. You could call it a flower pot shape, same shape. It's actually called a frustum, strange word. I'll pull up something on the web here. But the formula that I found was this one, pi over 12 times the height. This is diameter 1 squared, the product of the diameters, and whoops, that's supposed to say diameter 2 squared. That's a typo, so to speak. And that is the correct formula. I found it online in terms of the radius, which I'll show you in a moment. So a frustum does not have to be conical, as this one is here. It could also have a square base or some other shape. And they're using the letters capital R1 and R2 for the radii. And on Wikipedia, I found way more information than I ever wanted about frustums. And here's the formula for the volume in terms of the radii. Now, the radius would be 1/2 of the diameter, right? So for each of these terms, you'd pick up a 1/2 squared or 1/4, and that's what accounts for that 1 out front. And I was reading that some Egyptians knew about this formula over 2,000 years ago. They didn't have calculus back then, so who the heck knows how they came up with that? That's always a mystery. Aliens must have been those visiting aliens that showed them how to make the pyramids. And if you're wondering where else this shape shows up, evidently it's very common. Flower pots, the fairing between stages of a rocket, right here. And I read that it even shows up all over the place in computer animation. And maybe you're wondering, why would you ever need it? Well, you might need it to measure the density of ice, but as we're going to see in a moment, it really didn't work that well. I measured 546 grams for the mass. The larger radius was 10.2 centimeters, or diameter, I should say. The smaller was 8.6. And then this very uncertain value of 8.5 for the height. Now, I've already entered the formula for the density, and I forgot, I want to hide that so that you have to figure that out yourself. Hide the formula bar. You know what? If I hit enter, you'll see it all. So let's see. Okay. 0.923. 923 versus the accepted value, I believe, is 0.934. So we're not far off. But that's largely, I'm not going to say largely, but that may be somewhat due to good luck, accident. Because check it out, when I put in my uncertainties, there's at least an uncertainty of 1 gram in the mass. That 2 millimeters, I think, is fair for one of the diameters. Less so for the bottom. And then the height was definitely uncertain by as much as 0.5 centimeter. And I find a 12% relative uncertainty. Now, 12% of 0.923 grams per cubic centimeter. I should have said grams per cubic centimeter as the density there. That's an absolute uncertainty here, absolute of 0.11. So what I'm saying here with the spreadsheet is that most likely the density of that sample of ice that I just showed you is within, I'll say it this way, it's 0.923 grams per cubic centimeter plus or minus 0.11. And when I actually write that out explicitly, I get this very broad range. This is really not very precise at all. Now, it's encouraging that the accepted value, you can look it up, of 0.934 does fall within my range. So that tells me, it tells me that I conducted this experiment correctly, assuming that I actually had frozen water on that scale. But it also tells me that my experiment was rather imprecise. Now, does that mean I screwed up? Does that mean I did it wrong? I think what this is telling me is that I definitely did it right. See, I took all the uncertainties into account, and that is why my probable range for the densities does enclose the true value. Like I said, I got pretty lucky here. Based on this range here, with a slightly different choice of parameters or measurements, I may have come up with a value like 0.85 here. And if I had originally gotten 0.85, I would have said, okay, I did something wrong. I measured this wrong. But I really didn't. I did the measurements correctly. I'm just recognizing that they're uncertain. So now obviously, if you do something really sloppy, like say, hey, I think the diameter D1 is 10.2 centimeters, but I could be off by 5 centimeters, then that would cause a propagated uncertainty of over 100%. You get this ridiculous range of values. That's not very scientific, right? Or it's not a proper analysis. So you do want to try to make accurate estimates of your uncertainties. What if I decrease this to only 1 millimeter uncertainty? Because I was pretty careful in the measurement of both diameters. And I still find a range that encloses the accepted value. And so it's satisfying to see that everything works out well as long as you make the measurements as best you can and choose realistic uncertainties. Now, if you're wondering how I came up with the formula for propagated uncertainty, because in this instance, if you look at the formula I showed you, each diameter shows up twice. And it's not simply multiplication and division. There's actually multiplication in there and addition. That's a little more sophisticated. There is a formula that will encompass all situations. I haven't introduced you to that formula yet. It involves partial derivatives. So I used a simpler formula that actually tends to, again, perhaps overestimate the uncertainty in the final result. So if you need help, if you decide to do ice, maybe you think you can improve on my method and you need a little help with that formula, just let me know in an email. But the water seems to have been more successful. Ice, doing it with the ice actually was better for getting acquainted with the process of the error analysis, but the results didn't come out as accurate. Oh, there's my messy desk. You were not meant to see that.